Alright, so welcome back to part 2 of this video. So we kind of left off at this point. We kind of set up our equation for part B. We said sum of the forces in in the x component basically is equal to mass times acceleration in the x direction. So that's fine. And what I meant to say, I probably didn't word it quite so rightly when we left it off in part 1. What I meant to say was a common question will be that is this fx the same as the f net we found in A? So that's why I kind of like put a question mark there. I'm not saying that it's the same. I'm saying that this is probably a common question that comes across that students start thinking about, and the answer is no. So no, this is not the same as the f net we found. It's not 1.4 times 10 to the 5 newtons. 1.4 times 10 to the 5 newtons is the net force for the car and the locomotive, which is why we use the mass of the car and the mass of the locomotive, right? But in this case, as you can see from our free body diagram, we're totally not taking into account the locomotive at all. We're just looking at the car. So obviously, how can you use the same net force when we're not even thinking about the locomotive? So no, it's not the same F net. So that means there is an F net acting on the car. There's a specific portion of F net that's acting on this car, but we don't know what it is. So we find that out by very simply setting up an equation. So F net equals Ft, right? And I'm getting this from the free body diagram. There's two x component forces. There's an F net and there is an Ft. Now I don't necessarily show the F net on this. I don't need to show that, right? But I know that there's an F net and it equals mass times acceleration, and which also equals Ft. So F net equals Ft, and I also know that F net equals mass times acceleration. So this also equals Ft. Now when I say mass, I'm talking about the mass of the car. So we'll just write that down again, not the locomotive. So let's just write that down in the corner here. So we are not taking into account the mass of the locomotive. So just to make sure everyone remembers the next time they come across a problem like this. So we're left with something like this, and super easy. We've got all the values. We know the mass of the car, which, if everyone remembers, was 5.4. Oh, or not 5.4, 5.0 times 10 to the 5. And it's in kilograms. And the acceleration stays the same. It was 0.12. Remember, the entire system is accelerating at this rate, right? 0.12 meters per second squared west. And this equals your Ft. And essentially, once you plug this into your calculator, the answer you should be getting is roughly 6,000 newtons. So essentially your answer is 60,000 newtons is the force of tension. And again, we don't want to leave it as this, so we kind of we want to put it into its proper notation, scientific notation. So it would be 6.0 times 10 to the 4, because remember, now after the 0 I have after the 6, I have, I have to move 1, 2, 3, 4 decimal points. So 6.4 times 10 to the 4 newtons. Now, you don't have to worry about you can write the direction, sure, it's west, but you don't have to, because let's go back to the original question, and I seem to recall that it just asks for the magnitude of the tension, right? So essentially no direction is needed. But if you really want, you can still write it. So no direction is needed. But if you want to be picky, you want to be like, okay, I want to just make sure it's west. But your final answer, it would be perfectly all right if you just wrote 6.0 times 10 to the 4 newtons. Now, again, I can't speak for every high school and every teacher, but generally what, like the first unit they teach you in physics is, the significant digits and whatnot. So I know the school I went to and the teacher I had, if I left my answer at 60,000 newtons, I would lose a mark. I wouldn't lose all the marks because I have the right answer. I just didn't communicate the answer properly, because in the correct, or the, the nicest way, nicest way of putting the answer is 6.0 times 10 to the 4. So again, depending on your class, on your teacher, you'd go about, this thing at the end. But what I'm used to, and my style of doing these problems, I generally round my answers to whatever is in the thing. And I obviously spelled account wrong here, so ignore that, and just what I meant to say was account. So but you get the point, right? So this is how I would go through this problem. Once again, I don't think it should be much of a problem. We've done forces. If you've been to my channel before, I've done another forces and dynamics problem, and in my opinion, that one was a little more complex than this one. This is fairly simple, but if we go back, again, some tips. I got the same tips for everyone. Underline, the main numbers. That's the first thing I do. I read the question. I read the question pretty well the first time around, and the second time around, I read it even more slowly, and I underline, like, oh, I see numbers. What do these numbers mean? The units. You got direction, units, everything, and then again, little keywords in the question. So part A was asking you to calculate the net force. That's a keyword. You're looking for F net, for sure, of the entire train. So that's key as well. That means the locomotive plus the car. So L plus C. And then part B, determine the magnitude. Another keyword. That means, oh, okay, so I kind of don't need to worry about any directions or anything. So magnitude of the tension. So there's another keyword. So you're finding the size of the tension. That's essentially, you can read those two words, and you don't even need to read the entire question if you're kind of like running out of time. So keywords, pick up on keywords, right? Magnitude and tension. And just no direction needed, just a reminder. I don't know if a lot of you are familiar with this method. There's a lot of this method is called the guess method. I usually don't write G, U, and E because I've done so many of these problems, but I do start off with, listing the givens. So I write down my given numbers, and I write down, okay, what am I looking for? What is my unknown? So in part A, my unknown, which is, I wrote as U, is F net, right? So F net equals what? I don't know what it is. And then the E stands for your equation. So what equation should you be using, right? So in this case, F equals MA. And when you finish off the guess, like the guess method, so you have G, U, E, and then you have your, when I say S is essentially, the first S is your kind of like substitution. So when you substitute numbers into your equation, right? So it's not exactly this part. In this part, I was actually just explaining, like, okay, what is the entire system? But so your substitution would essentially be this part, right? So this would be your, the G, U, E, and this would be your first S in your guess, and this would be your final S. So this would be the statement, therefore, F net equals, or Fx equals 1.4 times 10 to the 5 newtons. This S, you can either call it substitution or you can call it solution. So this would be your solution, right? I sometimes forget, which was I was calling substitution, but it's absolutely fine. You can call substitution too. So this is your solution, this is your statement, and I went back and this is your equation, and this was your unknown, and this is, your given. So this is called the guess method. I'm pretty sure there's a lot of different ways. Some people call it the grasp method, and it's something like, I think they teach you like in grade 8 or grade 9 when you're learning like basic algebra, and it's handy technique, so later on, like even when you reach university, it's a good habit to list any details you get from the questions you got your given, and it's a nice way of setting up your solution, so it actually looks neat, and you can go back, and if you get lost, you can kind of follow through your own work. Whereas if you're just listing like random stuff, sometimes for the marker, they're like, okay, what in heaven's name is going on, and they might just lose you, and you might just lose marks for that. So this is just a nice way of setting it up. Part B, drew a nice little sketch in the first place, so we knew, okay, the locomotive is somehow attached to the car, and we talked about the tension, the force of tension being a special force. It's tension force, so think about pulling on a rope, and you're creating tension in the rope. But the only way you can create tension in the rope is by pulling. So tension forces are only kind of like pulling. You can't push something and create tension on it. So you have a rope. If I'm pulling on this side, so on the locomotive side, if I'm pulling, I'm going to be pulling towards the east direction, right? So which is this way. And if I'm pulling on the car, I'm going to be pulling towards the west direction, which is in the same direction as the F net, right? So which is why you think in part B that, okay, if you know, is the sum of the forces the same F net as we found in part A? And the answer is no. There is an F net, but like I said, it's the F net, just the F net that's acting on C. So, and when you write that out, it's just, you know, the mass of C times the acceleration on C, which is the same. The system has one acceleration. So the car plus the locomotive both have an acceleration of 0.12. So you don't need to worry about that. But obviously, when thinking about just the car, we only have to consider just the mass of the car. So if you kind of like take the mass of the locomotive in account here, you're thinking of the F net of the entire system, which we're not concerned with because the tension we're looking at is only acting, the tension in the west direction is only acting on the car. So we're not concerned with, so it's only on the car. We're not concerned with this tension, right? So we're not really thinking about that. So, you know, just basically how I would go through this problem, you know, sub in your numbers and get your exponents right. And then, like I mentioned, you know, try not to leave your answer as just 60,000. It's, in physics, that just looks, you know, it looks too big and bulky, and, you know, so just round it off to, you know, put in a scientific notation. And so just work through the problem like this. And it's one of the easier ones I've done. Like I said, if you've checked my other dynamics problem, that's a little bit more complicated. So if you can do that, if you follow through that perfectly, this should be a piece of cake. If not, you know, practice more questions like this. I'll probably will put up more, you know, dynamics and forces problems, is because it's one of my favorite units, and I just, you know, I had a fun time, you know, studying that in high school myself. And it is one of the really important units in physics. You know, let's be honest. It's what teachers spend most time on, and it is probably the one that gets a lot of students, you know, like, oh, I hate physics, you know, why would anyone study this kind of stuff? But once you get really comfortable with these kind of, with Newton's laws and kinematics especially, those are like the kind of like the introductory units to physics. And if you hate those two, you kind of start hating like the entire physics course. But if you know, and if you like love those two units, you kind of like breeze through the rest, because the rest of physics is just really easy, right? And these are the most comprehensive parts, I guess you could say. So you know, keep on practicing your work. If you have any questions, you know, feel free to leave any comments in the comment box. If you really like my channel and it's really helpful, you know, feel free to subscribe. You know, it's all up to you guys. Otherwise, just keep on visiting, and, you know, like, I'll probably have like more videos up pretty soon. You know, whenever I'm not busy, I try to make these videos for you guys. So have fun, and I'll, you know, see you guys next time.